Hello ladies and gentlemen. This short video is going to give you a brief introduction to density curves. And what we mean by density curves are curves that have certain properties. But we'll start out with the vocabulary, and what we'll be using in this one particular video and in your explanation of density curves are shape, center, and spread. Yeah, those again. The mathematical model of it, what a density curve is, what a normal curve is, and then obviously we'll use some of our definitions, or we'll use the vocabulary of right skewed and left skewed in our discussions in this video. Okay, a density curve. If we took a histogram that represented all of your data, 100% of your data, and tried to draw a curve around the top of it, touching all of the tops of the bars of our histogram, then we could claim that that would be a density curve. Okay, so we'd have to draw a nice smooth curve, and because the bars of our histogram are not all the same height, it would be very difficult for us to touch all of the bars when we try to draw a smooth curve around it. If you've this curve represents an ideal situation, and we call it a mathematical model. If it represents an ideal situation, it models some concept that we are trying to get out to the population, and this is called a mathematical model. The area underneath the curve. We can imagine that finding the area underneath the curve in statistics is like using a Riemann sum in calculus. And for those of you who have never had calculus, let me explain this. When we try to find the area underneath a very weird curve in calculus, it's almost impossible. But a gentleman a long time ago said, hey, you know what if we stick little rectangles underneath the curve? Sure, some of them are going to stick over the top of the curve, some of them are going to stick underneath the curve, but if we found the area of each one of those rectangles, it would come pretty close to the area underneath the curve. And if we made the width of those rectangles smaller and smaller and smaller to where they're teeny tiny, so we have almost an infinite number of rectangles underneath the curve, then those gaps that we miss when we draw the curve will be minimized, and so the area underneath the curve will be almost perfect. We'll have a little bit that sticks over the curve, a little bit that sticks under the curve, but when we add up all of those areas, it would capture the area underneath the curve. And the gentleman was Riemann, and we use that very often in calculus when we integrate. But we can also use something very similar in statistics. Now, statistics, when we draw our curve over our histogram, it's very rough. I mean, we talk about it's approximate. And so we have a lot of area that we miss, but we also have some that we go over. Underneath the curve in statistics, though, all of our data is there. So the area underneath the curve, we already know the area, and that's 1. It's 100% of our data. But very often we find ourselves looking at portions of the curve underneath, and we're forced to go back and look and think of it again as histogram, and we have to find the area of those rectangles or bars. So keep that in mind as we're trying to find values, percents of area underneath the curve. So there are only two criteria that we need for something to be a density curve, and one, everything always has to be above the horizontal axis, and it has to have an area that equals 1 underneath it. Okay, and I give you two examples here from figure 2.5 A and B. We have the median and mean of a symmetric density curve, what we have always known as the bell-shaped curve. We will come to know that very soon as a normal curve because it is symmetric. And we notice that the mean and the median are in the same spot. Figure 2.5b, the mean and median of a right skewed density curve, and we see that once again the criteria means that the curve has to remain above the horizontal, and the area underneath the curve has to equal 1. We've discussed this a little bit before, but when we look at the median in this particular curve, it's to the left of the mean. Why is that so? Well, we have values that are pulling that curve to the right. So there are some extreme values out there to the right, and whenever we have some very high values and we put those in our average or our mean, then that mean gets pulled to the right of the median. It gets pulled closer to those extreme values. So here's a very good visual that represents that. Okay, so this is all I need to say about density curves. You have enough information now to proceed to the assigned problems, and I thank you for giving me your attention.